Now we're going to continue our exploration of series and integral applications. And we're going to see one of the applications of the series that we have done in the last 2 days. In this video, we compute the mean of the geometric random variable x. So when we have a geometric distribution, we keep doing the experiment over and over until we reach something. That means if we do it n times, we fail n-1 time, and in the nth time, we make the success. And in this case, we can say that the probability distribution of our experiment can be given by 1 minus p to the power x minus 1 times p. Okay, x is a positive integer. That means we failed x minus 1 times, and in the x time we have succeeded. Okay, in our case we want to find the mean. Okay, and to find the mean of this geometric random variable x, we will have to deal with some computation of some values that we have to deal with them in the correct manner. Okay, let me switch something here. Okay, let me use k here to make it look like something familiar. Okay, here k is 1, 2, 3, and etc. K is in n. Okay, so to compute the mean, we have to compute this sum. Okay, k times 1 minus p to the power k minus 1 times p, where k is going from 1 to infinity. So this is the mean. Okay, if we try to compute this one here, we will see that we need to have some formula for that. Okay, and there are many ways to do so, but the key is that we remember from last time when we talked about series, Taylor series, we have expanded 1 over 1 minus x as 1 plus x squared plus x cubed, etc. And we can write it in general as the sum x to the power k. K is going from 0 to infinity. Okay, and we said that the radius of convergence of this series is between minus 1 and 1. Okay, so this is the interval of convergence. The radius is 1, to be clear and to be precise. Okay, now what relationship can we make with this one here? Okay, we can use a key idea is that when we have a series that's convergent, its derivative, the series, the Taylor series, its derivative will have the same radius of convergence. Okay, so here we can differentiate this one here without worrying, because we can differentiate term by term. Okay, so this means that I can do the following without worrying. Okay, d over dx over 1 minus x is d over dx, the sum of x to the power k, k going from 0 to infinity. Now I can enter this differentiation inside even if I have this series. Okay, I can have the following, the sum k going from 0 to infinity of d over dx, x to the power k. Okay, now what's this one here? Clearly we know that that's 1 over 1 minus x squared. Okay, oh sorry, here it's 1 over 1 minus x. Okay, so it's 1 over 1 minus x. You see it from here. I take the derivative of both sides. Here I get this one clearly. We know how to differentiate 1 over 1 minus x. Here I I get something like this, k going from 1 to infinity of k times x to the power k minus 1. Okay, because when we differentiate this one here, the 1 will go, and we're gonna have x is gonna be 1. That means we lost 1 degree. That's why we start from k going from 1 to infinity, and this degree that's lost, you see it on the power of x. Okay, so now how can we use this one here to compute this sum here, the mean of the geometric distribution? Okay, we see that if we let, okay, the key idea here is that these x's are in minus 1, 1. So if we let x equals 1 minus p, and this is this is still in this interval because p is between 0 and 1. Okay, 1 minus p is still in this interval. Okay, and if we plug it here, on the left side we're gonna have 1 over 1 minus 1 plus p squared. On the right side we're gonna have the sum k times 1 minus p to the power k minus 1. K is going from 1 to infinity. There is one thing missing here, this p here. Okay, we have to multiply by p because we don't have that one here. Okay, so here on the left side we're gonna have 1 over p squared, and on the right side we're gonna have the sum k 1 minus p k minus 1. K going from 1 to infinity. Now what's missing now? Missing this p here. Okay, look, this p, it's not here. So if we multiply by p, we're gonna have 1 over p is equal to the sum of k times 1 minus p to the power k minus 1 times p, k going from 1 to infinity. Okay, and what's this one here? This is the one that we are looking for. This is the mean. Okay, therefore the mean of a random variable, geometric random variable, is 1 over p. Okay, and this is the geometric distribution here. Okay, it's positive. We can prove that it's 1. Okay, this one here, prove that this is 1. It's positive because it's the product of positive numbers. So the next question is prove that this one here is a density function. Okay, so in this case, when it's discrete, we call it probability mass function. So we need to prove that in the case of a geometric distribution, this is a probability mass function. We're gonna prove it later because we need to apply the series. So here we apply this notion of the series here to get our mean for the geometric random variable x. Okay, you see how this one is helpful. We will come back and explain why we are allowed to differentiate series, okay, term by term, when we have the same radius of convergence. Okay, the derivative and the original series, Taylor series, they have the same radius of convergence, and therefore we can differentiate and integrate term by term. Very critical and important result. Okay, so this is one application that we used here. If you see any errors or mistakes, please let us know. Please like, share, and subscribe. Thank you again.